And we are back for another video lecture, Chapter 8, Section 8, Calculus 2, the study of improper integrals. And now I have all my little calc babies tuned in, ready to learn. So this is the last section of Chapter 8, something we've been building up to get to. And it has to do with the idea of definite integrals. And the idea of areas under curves. And this is actually really interesting, a very, very interesting lecture. So let's kind of think back to what we have learned, right? We know that for definite integration, right, when we have our integrals are set up with upper and lower bounds, that we can think of that as finding the area under a curve, right? And that curve is, of course, the curve of the derivative. Now, a couple things that was required, right? So, for example, the fundamental theorem of calculus required that the function, the derivative, be continuous from a to b. All right, that was one requirement if you want to use this definite integration process. The other requirement was that the interval from a to b actually be finite. So let me just really quickly make sure you understand what I'm talking about. So if you saw the bounds, let's say you saw the integral from 0 to 2, right? That would mean that we are trying to calculate the area under a curve from x is 0 to x is 2, right? Since we are integrating with respect to x. So that's what I mean by this point right here, that the interval from a to b has to be finite. Now, where do we go from here? Well, here's what's a really interesting question. What if, for example, let me just draw something, okay? What if the curve looked like this? And here, instead of asking, what is the area from A to B? What if you wanted all of the area? Right? What if you wanted the entirety of the area under the curve? Well, would that be just infinite area? Maybe. Possibly. Or is it possible to find the entirety of that area under a curve that actually is a finite area under there? And if that is a finite area, how can we actually find it? Well, that is the study of this section, right? So it's very, very interesting. We want to take a look at what we call improper integrals. And improper integrals are going to look something like this, right? We're going to go from, I don't know, some bound a to infinity, or we're going to be going from negative infinity to some bound, or even what if we want from negative infinity to positive infinity? Very, very interesting. And that's why we had to have a grasp of 8.7, the idea of L'Hopital's rule and limits in order to make this work. So for this video, let's just explore a little bit, okay? So let's just put our pens down, put our phones away, and let's just explore a little bit. So let's take, for example, my example that I've written here, that I want to integrate 1 over x squared with respect to x from 1 to, well, I didn't label this. I didn't actually put a constant here, just 1 to some value we're going to call b, right? So how would that look? Well, let's think about it. So if to integrate let me go ahead and start this integration process, and then we'll worry about that b and what that means to us in just a second. So of course we can rewrite this as the integral of x to the power of negative 2. And we can go ahead and integrate this, which means we're going to x to the negative 2 plus 1 over negative 2 plus 1. And the result is negative 1 over x. And of course, you know the deal. We still have to use our substitution to go from 1 to b. So f of b minus f of 1. Let's go ahead and do that right now. So if I start with f of b, that would be negative 1 over b. Okay, so that is f of b minus, right? So minus what? Minus f of 1. Okay, well, in this case, f of 1 would be negative 1 over 1. And now let's just rewrite this. So we end up with, I don't think you'll argue with me too much here. We end up with, obviously, the double negatives turn, and 1 divided by 1 is just 1. I'm just rewriting these in a different order. So this is going to be 1 minus 1 over b. Okay. So now let's look at the graph off to the right here. So this is the graph of 1 over x squared. And just recall, right, that this is the derivative. And when we use definite integration, we are finding the area under a derivative. At least that is the goal, is to find the area under a derivative. Now, the bounds start at 1, so you're kind of seeing this vertical, I'm looking at the graph, so you're kind of seeing this vertical line at x equals 1, and then there's just some arbitrary x value that we're going to call b. I hope that makes sense, that in this case, b has no special significance. It is just an x value, okay, to the right of 1. Now, can we agree, so I'm going to kind of go ahead and shade in some stuff here, that we would be finding the area under this curve. And let you and I agree that if I could drag and drop this this value b, like if I could move it, in other words, well, as I move it to the right, ask yourself, should the area under the curve increase or decrease? Well, yeah, it should increase, right? So as I continue to move b to the right, I'm collecting more area under the curve of 1 over x squared. But I want this. What if I want to move this value b all the way to the right? In other words, I want all of the area under this curve from 1 to infinity. So here is the good news. First, let me rewrite the question. So remember, we started off with b is just some constant, but you insisted that you weren't satisfied with the area from 1 to b. You wanted the area from 1 to infinity, right? The entirety of the area. And here is the gist of this section. So how do you answer this question right here? Well, You do so by simply taking the limit as b goes to infinity. Of what? Of the 1, right, it's coming up from over here, of the 1 minus 1 over b. Are you with me? That if you want to answer this question about the area, from 1 to infinity, it's the equivalent of asking the question of what is the limit of 1 minus 1 over b as you allow b to go to infinity. Okay, now this is right out of last section. Well, if we, again, just whatever it means to say, to substitute infinity, we would end up with 1 minus, let's say, 1 over the infinity. And remember this, if you divide up $1 an infinite amount of ways, then no one's going to get any money. So this ends up just being 1 minus 0, or here we go, there's your answer, 1. So what was the area under the curve of 1 over x squared as from 1 to infinity? There it is. It's an area of 1. Now, units, we haven't specified units, anything, but that is the gist. And so what you're seeing is we can find these improper integrals really come down to just simply looking at the limit. Okay, now we're going to use two terms in just a second. We're going to use the words converge or diverge, right? Does the area converge or does the area diverge? And we're going to define those in just a second. But let me go ahead and show you. So take a second. I know that I've placed a lot on this slide. So bear with me here. Don't feel like remember, you can always pause the video and write some stuff. But what I'm trying to do on this page right here is to make sense of the 3 types of improper integrals that we're going to be, 3 types of improper integrals that we're interested in. And I just want to take a look at what each of these mean. Okay? So first let me read the key idea to all of this whole section. And the key idea is this. Look, the integral converges when the limit exists. Right? So let me go back to that last page. So you agree with me that the limit exists in this problem, right? It was equal to 1. So the limit exists, thus the integral converges. That means you actually can find the area. Now, the integral diverges when the limit does not exist. And in this case, what we mean by diverges, right? So diverges for our purposes, did I even spell that right? D-I-V-E-R-G-E-S, I think I did. For our purposes, diverges is an infinite area. How's that? So if the area under a curve is infinite, then the integral diverges and the limit does not exist. That's the key idea. Now, let's now take a look at each of these 3 improper integrals one by one. And let's start with the first one. Now this looks very similar to what we did on the previous slide, right? So in this, if you want to integrate from a to infinity of some function, that's kind of like when we were trying to integrate from 1 to infinity of 1 over x squared. That's the equivalent. Then as long as your function is continuous on that interval, a to infinity, right? So the continuity just means, look, like I hope this makes sense. I don't want to take away that when you're discussing area under a curve, we have to assume that your function is continuous throughout that interval, right? It can't, you can't have vertical asymptotes and jumps and various discontinuities and still expect to be able to find the area, right? So for just an informal way, if you can draw the curve without ever lifting your pen, right? Very informal, very sloppy, but if you can draw it from a to infinity without lifting your pen, then it is continuous over that interval, right? From a to infinity. Now, what I'm doing now is I'm showing you just the graph of the type of area you're looking for, right? So from a to infinity basically means you're trying to find all of the area under the curve from a to infinity. Now, part 2, it says if, again, assuming that your function is continuous from negative infinity to some value b, then notice what we're doing here. You're looking to find the integral from negative infinity to b. How do we do that? Well, we're just going to start by choosing some random value to the left of b. Okay, they're calling that a. And then we're going to let a go to negative infinity. Right? So it's like it's the equivalent of say, hey, let me just find some value that I'm going to call a. I'm trying to write, but it's not quite working very well. Right? it's the equivalent of say, okay, here's some generic x value that I'm going to call a. And now I'm just going to, since I want the area under the curve from b to negative infinity, or I should say from negative infinity to b, then I just let this value of a go to negative infinity. Okay? Just notice the main thing is notice the limit. Notice what you're doing with the limits along the way. Now the last example is when you just want the total area under the curve, right? You want all of it. And in this case, I just use the same graph over and over again for each of these 3 examples because really all I'm doing is showing you the shading. Now, whether the area actually it converges or diverges is to be determined. I'm just trying to show you what it is that you want. So for the last example, notice that you're trying to go from negative infinity to positive infinity. You want the total area, right? And the way that we do that is, well, we're going to choose some value c. So let me read this. So, of course, your function has to be continuous from negative infinity to positive infinity. But there's no stipulation on the value of c. Right? So notice it says c can be any real number. So what you choose for your value of c is quite irrelevant because you're going to let c go to what? You're going to let c go to negative infinity, or you're going to let c go to positive infinity. And now you're just going to take the sum of these two. I hope that makes sense. So step 3 is kind of like taking, or I should say formula 3, definition 3 is kind of like taking the sum of definition 1 plus the definition 2. All right. So there's nothing left to do except to jump in and start trying some, right? So now just remember, we say the integral diverges when the area is infinite, right? So diverges, for our purposes right now, is just an infinite area. Ready, so let us begin. So we want to evaluate the integral from 1 to infinity of dx over x. So let me rewrite that. Let me rewrite that. So that's just, we're going to be integrating the integral from 1 to infinity of, and I'll write this as 1 over x dx, right? No need to have the dx in the numerator. Okay, so notice that this looks like the first definition. So in this case, we're to approach this. This is the equivalent, right? My dog is barking at cats, random cats that are walking up and down the street outside. So we'll have to just have to put up with that. That's okay. So what are we asking? So we want the limit as b approaches infinity. I'll tell you what, if you don't mind, while my dog finishes barking at the cats, if you don't mind, let me go ahead and rewrite this down here. So let's rewrite that as the limit as b approaches infinity of 1 to b, from 1 to b, 1 over x dx. Okay? So what have I done? I'm just saying, what I'm doing is, this is what the problem asked of us. And I'm saying that equivalent to this is to simply ask the limit, a limiting question as b approaches infinity of the same, of 1 to b, 1 over x dx. So let's go ahead and finish this up. So we're going to start by integrating. So let's go ahead and write limit b to infinity. And ready, let's go ahead and integrate this. So if I integrate 1 over x with respect to x, then that is simply ln of x. Right? And of course, I still have to back substitute. I'm going from 1 to b. Ready? So this is the limit as b approaches infinity of ln of b minus ln of 1. Okay, and now there's nothing left to do except the definite integration portion is done. So there's nothing left to do in this problem except to evaluate the limit, right? So this is let's see. So this is ln of b minus 0, or minus, yeah. So actually, let's go ahead and do that. So the limit as b approaches infinity, ln of 1 is just 0. So really, it's just the limit as b approaches infinity of ln b. All right. So what are we looking at here? Well, look, if ln, if you start plugging in larger numbers for ln, the output is going to continue to be larger numbers as well. In fact, if you were to think about ln of the infinite, you would actually just get infinity. So what does all this mean? It means that the area under, let's look up here, look, the area under this curve from 1 to infinity is infinity. So to talk about an infinite area means that, so in this case, the limit does not exist, right? Infinite limits are not limits. They do not exist. In fact, the infinity is telling you why it does not exist. It's unbounded, right? So the limit does not exist. Therefore, the integral, that's, by the way, that's not how you spell integral. Therefore, the integral diverges. All right, we'll take a break and we'll come back.